Okay, let's go ahead and jump right in. We've got quite a bit of material to cover. Today, the overall focus of today will be now integrating all of the pieces, the building blocks, the alphabet, if you want to think of it that way, of elementary steps, and stringing them together into productive catalytic cycles with synthetic applications. We'll build that up really from the ground up by discussing first the fundamentals of catalysis, of ancillary ligand design, and then from the next lecture forward, each day we'll really focus on one specific category of catalytic transformations. So we left off and had a bit of material still in the carbene section. So we'll just wrap that up quickly and then jump into the main focus. So let me share my iPad here. So we had concluded yesterday's class with discussion of or Tuesday's class rather, of discussion of Fischer Carbene reactivity, and specifically the last example we covered was this Wolff-Dutz reaction, which is a 3+2+1 cycloaddition to make highly substituted phenols, a reaction that's stoichiometric in the metal, and I think that's a common theme as we talked about in Fischer Carbene reactivity. Cool reactivity, difficult to turn over for various reasons. I think principal among them, the difficulty of being able to generate the Fischer carbene under reaction conditions that are compatible with catalytic turnover. So now let's look at the other end of the carbene reactivity spectrum, Schrock type carbines. We had introduced the first known Schrock carbene in our discussion of alpha elimination as an elementary step, so I won't rehash the details here. This was first discovered by Shrock in the context of his explorations of polyalkyl tantalum complexes, and that was during his time at DuPont. Let me close that, zoom in further. So in terms of structural features of Schrock type carbines, let's now consider a relative of the first Schrock carbene that is a bis CP analog that has a methylidine as the carbene and then a methyl group as the fourth ligand. So if one inspects the crystal structure of this complex, which is known, the metal carbon bond distance is significantly shorter than what we saw in the case of the Fischer carbines. And here we almost have like a built-in internal standard here for what a prototypical alkyl tantalum bond should look like. So significantly shorter now than tantalum carbon single bond. As a reminder, the Fischer carbene, the representative example we covered, had a bond distance of 2.13. So consistent with this general trend that Schrock carbines have stronger carbon metal bonds, and that manifests in terms of structure as being shorter. So let's now consider reactivity of Schrock carbines, and to do so, we will jump over to problem of the day number 3 from last time, which is restated here if you don't have your worksheet handy. So in this system, we take bis CP titanium dichloride, we react it with trimethyl aluminum, and we get this new complex. And again, touching back to the themes we covered in main group organometallic chemistry, this is a bridged structure where the methyl group is a 3 center 2 forming a 3 center 2 electron bond across one titanium and one aluminum. Okay, so now upon treatment of this complex with Lewis base, so one option is to have it in THF solution, or another option is to use pyridine. Even catalytic quantities is enough that will react further to give a new species, and that can react with carbonyl compounds or with alkenes. So Seung-Han, are you there?
Yeah.
Okay, walk us through what might happen here.
I guess the ligand will, the THF and pyridine will exchange the ligand on the metal.
Okay. And what will then transpire?
I'm not pretty sure, but I guess the chloride will be displaced.
Okay, I think your intuition here is totally on point. The point of the Lewis base here is to break up this aggregate. So the question, I guess, is what is it going to be broken up into? Anybody want to jump in with an assist for Seung-Han?
Is that a titanium carbine?
Okay, beautiful. So this reagent is called the Tebbe reagent. And upon treatment with Lewis acid, this will break up the bridged form and give a titanium methylidine. Now let's think back to what we covered last time about general Schrock reactivity patterns. You have a carbene that is nucleophilic at carbon, electrophilic at the metal. So what do you think, Seung-Han, maybe just the first one, what would happen? How would you expect something like this to react with a carbonyl compound?
So I think the carbonyl will undergo a metastasis, and the oxygen will be displaced to methylene.
Beautiful. Okay, so let's unpack this step by step, just in case anyone is not sure. So the first step will be formation of this oxa-titanocyclobutane via a 2+2, very much in parallel to a Wittig type transformation. And then, as Seung-Han said, this will collapse. So the end products will be conversion of the carbonyl to a methylidine. And then what is the byproduct on the metal side, Seung-Han?
Titanium oxide.
Beautiful. And so formation of titanium oxide provides a strong thermodynamic driving force. And maybe one more question on this, Seung-Han. So would you expect this reaction to be able to be turned over catalytically? And if so, why? And if not, why not?
I think if the reaction wants to be can be recycled, then there's some reductant to reduce the titanium oxide and back to a carbene.
Exactly. You pinpointed the challenge. So this is a reaction typically performed stoichiometrically. There may be some rare exceptions where it could turn over catalytically, but it's challenging because you have a strong thermodynamic driving force to form the titanium oxo complex. And then to regenerate the methylidine, you need to pay that same price. Now uphill, so you need to reduce it. You need a reducing agent that's strong enough to get back uphill, but is not going to directly reduce the carbonyl, for example. And that's a fundamental challenge.
Kiri, can I ask a quick question? Maybe it should be more obvious to me, but can you just quickly explain how the Tebbe reagent, upon adding the Lewis base, generates the carbene in terms of like electron pushing and what everything else is going on there?
Sure, I can do my best here. Well, let me provide one additional example, and this might help clear things up, Brendan. Maybe I'll put this piece of information on, and then I'll let you think about it, and then we can follow up. So there's another, this reagent can also be generated from another precursor. Does anyone want to jump in if you've seen this before? Very closely related. This is a dimethyl titanium bis CP complex called the Catalysis reagent. And the advantage here is you don't need any, there are two advantages. One is you don't need Lewis base. It just does this upon heat, and it does so by loss of methane. So this can be thought of as sort of a concerted deprotonation, sigma bond metathesis type process, or you could draw it via an alpha elimination as well. Another advantage of the Catalysis reagent in comparison to the TEBI reagent is that it's much more modular in the sense that it's easy to vary this methyl group to an ethyl group to a propyl group, because you're just adding that in the form of an organometallic. Whereas there are relatively few trialkyl aluminums that are commercially available, for instance. So I think in this case, well, yeah, it's interesting. Maybe in the case of, I'd have to maybe double check this, and Van, you can chime in if I've got this wrong. In the case of where the Lewis base is also somewhat bronze cytostatic, like pyridine, that might participate in deprotonation. But I think the first step is you can, pyridine will coordinate to aluminum and break up the dimer, and then now there are different ways you could draw this elimination happening. It could be loss of HCl, for example, that could be assisted by the Bronsted base, or could be non-assisted if it's in THF.
Yeah, I don't think you need loss of HCl because this methyl here is like CH2. Is it CH3 already? Oh, I see. Because of the other H. Yeah, I know this reaction definitely doesn't work without the Lewis base. Yeah, I think what you said in the beginning is right, Carrie.
Okay, now let's consider the other option. So this is, I mean, I thought this problem would be interesting because it shows, the most classical reactivity that is really textbook with TEBI reagent, and then also something that's so new that it's on ASAPs, which is this report from the Frederick lab at Florida State. So Tim, what do you think might happen here?
So I think that it would also do a 2+2.
Okay.
And at this point, I think you would have a like a same type of complex that you drew with the titano-oxo, except instead of the oxygen, I think you'd have another methyl group there. Yeah, and then maybe this could be catalytic and do reductive elimination to form the cyclopropane.
Okay, so first step is formation of the titanocyclobutane via 2+2 in analogy to what we saw before. I'm on board with that. And then let me just make sure I follow what you said. So this would be D. This is A, just in case anybody is going through this. Okay, so then the way I have this drawn is that this is formed as an intermediate, and then there's a discrete step where you add TFA, which I should have drawn here. Sorry about that. So, and you said that this could reductively eliminate potentially to form the here and here to form cyclopropane, which I think is plausible. But what else could happen? If you have this dialkyl titanium, you treat it with reasonably strong acid, what might you expect to happen? Remember, titanium is a pretty electropositive metal as the transition metals go. So an alkyl titanium is going to be more Grignard-like than it is going to be, alkyl palladium-like.
Okay, then.
More Grignard-like than more CC-like.
Then I guess it would just do a homologation, like net product.
A homologation. What would the product be?
Would it just be instead of a methine, would it be like an ethyl, or?
Oh yeah, so you were right as I have it drawn, but I drew the wrong. I managed to confuse myself. Sorry about that, Tim. I think I misrepresented what you told me. So probably if you were looking at this with some trepidation, this 2 + 2 is, given that titanium is large, it's going to want to go in this direction. Okay, sorry, but that was a copy paste error. So then from here, Tim, what would you expect the product to be?
Oh, would it just make the geminal dimethyl?
Very good. So we have these two getting doubly protodemetylated. And then what would the byproduct be, Tim? The metal containing byproduct.
I'm trying to remember the structure of TFA. Would it form like some eta 3 kind of owl type, or just like CP2 TI TFA2?
I think you're on, yeah, exactly. Okay, first you were overcomplicating it, and then you got there. So just like the starting material now, but with TFAs having replaced in the net the chlorides. Okay, and so this is also a stoichiometric reaction, and here would be a slightly different challenge for turning it over, which is that you would have to be able to have this system, be able to perform salt metathesis, counter anion metathesis, and then also have everything exist in the presence of the alkyl aluminum reagent. So the overall transformation is a hydromethylation that is Markovnikov selective, a pretty difficult transformation. I think the state of the art is methodology from the Barron lab in HAT mode. Any questions on this?
Oh, Carrie, I checked this. So it is methylene between titanium and aluminum, so CH2, which means I think that the Lewis base just plays a role in stabilizing aluminum, so it doesn't have to bind to the titanium carbene to be more stable.
For this for F, why is it not CP2?
That is because of a typo. Thank you,
Okay.
Alex. That's good. I can't get anything past you all, which is, I wouldn't have it any other way. Okay, any other questions on this? Okay, so that was sort of a introduction by fire to Schrock type carbene reactivity, and I think here you should be thinking about carbonyl type chemistry, and again, an analogy to the Wittig reaction. So as I mentioned in last class, these two extreme representations of Fischer type carbene and Schrock type carbene are important for bookkeeping, and because it does have predictive value in terms of reactivity trends, but there's a lot of chemistry and a lot of interesting, important chemistry in the middle. And so there are these so-called borderline carbene cases that I think sometimes get glossed over, but actually this has become in the last 20 years, I think, of fundamental importance to organometallic and organic chemistry. And so in these cases, it's not necessarily clear cut how you should electron count. These are things that maybe we wouldn't really ask on an exam, but and you can count them either way and think through in your mind what makes the most sense. So these borderline cases, I don't necessarily find this in a textbook, but I think this, in my experience, is the case. It seems to be the most common for group 8 metals, ruthenium and osmium. Some of the early work in this area was done by Warren Roper, and both with ruthenium and with osmium. So let's just consider one case. I don't want to get drilled too much into this reactivity, some of which is a little bit exotic. So here's an example of a osmium methylidine complex. That is generated from the precursor shown. One question you might have is how do you generate such carbenes? We've talked about some strategies, but from the precursor drawn, does anyone have any thoughts about how you might, what reagent might fulfill this role, just sort of accounting for the atoms involved? What do you think, Omar?
Are you saying where's the source of methylene?
Yeah. So overall, what happens? You basically are losing a phosphine and you're adding a methylidine. So what would be the source of methylidine potentially?
Maybe you can use yeah, I'm not quite sure, but
if I asked you, give me some CH2 in a bottle, what reagent would you pick out?
Oh, maybe, sorry, I'm blanking on the name. Is it diazomethane?
Got it. So that's a common, particularly in these group 8 metals, common way to generate the carbene is through diazo decomposition. So here, just from diazomethane, but you could also do this from to transfer benzylidine, for example, or other alkylidines. Great, Omar. And so here's the schizophrenic reactivity of these intermediate cases, which you can think of. I think this is terminology from this Roper paper that cited metallo-olefins. On the one hand, it can be nucleophilic at carbon, and here is shown engaging SO2. It can also engage proton to give the product on. And on the other hand, it can be electrophilic, so it can be attacked by isonitriles or CO, for instance, to give the other structure drawn. And this somewhat schizophrenic reactivity, I think, manifests itself most powerfully, which we have a whole lecture on this, so I won't cover it, but just want to make this connection briefly in the Grubbs catalyst series, where the most notable part of the Krebs catalyst is their functional group compatibility. Unlike most other metal carbene complexes that react with olefins, the Grubb series does not really react with carbonyl compounds to any appreciable extent, and that stems from this schizophrenic borderline type reactivity. And so you don't need to necessarily jot this down because we'll cover the mechanism in detail, but these 16 electron Grubbs pre-catalysts, they all share this general design. Initiate by loss of a ligand to form the active propagating 14 electron species, and then now a theme that we're starting to see, 2+2 to form a metallocyclobutane, and then retro 2+2 in this case. Okay, and then the last thing that I will cover here, and really admittedly not in much detail, really just to sort of get our accounting principles in terms of the electron counting that's going to be involved, are other metal carbon and metal X multiple bonded species. And so just like metal double bond to carbon, you can imagine metal double bond to nitrogen, metal double bond to oxygen. The world is your oyster. And so just to go quickly through, if you encounter such species, how you should electron count them. Metal double bond to nitrogen, these are called amidos, and they come in two flavors, either the bent form or the linear form, and normally in the a three-dimensional drawing of the complex, it will be specified structurally which one is at play. And I like to just draw out the Lewis dot structure because it's helpful to me to think about what's going on here. The bent one should have a well-defined lone pair on nitrogen. The linear one, the lone pair is engaging in so much pi bonding to the metal that actually it's rehybridized to sp hybridization, and I've tried to represent that here. Sometimes it will actually be drawn like this, but more generally it would just be drawn as linear form when you need to infer that this is what's going on. So in terms of the electron counting, the bent amidos here will count as X2, and then the linear amidos will count as X2L. And again, I think the L part of it sort of makes sense if you think of the lone pair as being the part that's participating in this way. And then they will be 4 electron and 6 electron donors respectively. There are also metal triply bound to nitrogen called nitrido, and these are X3. These can be important intermediates in N2 activation, for example. So these are X3 and 6 electron. And then in direct analogy to what we just saw with nitrogen is the same sort of treatment with oxygen. So metal oxos can be, unless otherwise specified, you should assume that they're X2, kind of like just having 2 hydroxide ligands or 2 alkoxide ligands, but hybrid, combined to the same atom, 4 electron. And then in some more exotic cases, actually a lone pair from oxygen can likewise donate in. And often this will actually just be drawn out as triply bonded for clarity. And in this case, it would be a LX2 ligand, just in direct analogy. So here's an example from the group of Terry Collins, this TAML manganese oxo complex, just to with a reference to sort of contextualize what I mean here when I talk about triply bonded oxos. And then a very brief point that I've made here to the side is that in the absence of a bulky, well-defined supporting ligand environment, a lot of oxos and amido complexes are highly bridged. I think this is best exemplified in the case of titanium oxide, which as we all know is a solid state material. And so this can also provide extra thermodynamic driving force in reactions like we saw with Shrock carbines, because depending on how the things react further, they can actually just polymerize or oligomerize in situ after engaging in as O atom acceptors. And then to review, we talked about vinylidines and these carbenoids that are typically generated from diazos. And then in terms of electron counting, when you see these, just think Fischer carbines. And then in direct analogy to Fischer and Schrock carbines, there are Fischer and Schrock carbines. Same logic in terms of early versus late transition metal, in terms of the substituents that are involved on the R group. And then the difference here in terms of electron counting is that in both cases, you've got one more X type. So LX in the case of Fischer alkylidine and or carbine, and then X3 type in the case of the Schrock alkylidine or carbine.
Sorry, a quick question about the vinylidine.
Yes.
Yes, so I'm not really understand why would you expect it is more like the Fischer carbine, because if the R1 and R2 is not a heteroatom, would it more like be a Schrock type carbine?
Yeah, I think there are two factors at play. It's great question. The first factor I mentioned very quickly in the last class, which is that vinylidines in their free form, the singlet state is significantly more stable than the triplet state. So this stability translates to some extent when it's in terms of its bonding preference when it's engaged in the metal. And then the other thing is, I think in general, I don't want to overgeneralize, but I think in general, you observe vinylidines. The most common synthesis, as I mentioned, is from terminal alkynes. And I think that's most common with late transition metals. So you have a periodic table, part of the periodic table argument, and then you have this other argument about the free vinylidine character. Does that make sense?
Yeah, okay, thank you.
Okay, super. Let's very briefly go through problem of the day number 4 from last time. Just some electron counting to make sure everybody's on the same page here. Carter, how about this first one?
For the first one, the coordination number would be 5. Oh, I guess if BARF is coordinating 2, then
BARF is outer sphere.
Okay. Then coordination number 5. It'd be
so how are you getting 5, Carter?
Getting 5 from 2 lone pairs from the I guess the enolate kind of species.
Okay, maybe first let's take a look at this carbene. Is this going to be Fischer type or Schrock type?
It has the oxygen in the R position, so
that's an argument for what type? Yeah, pi donating.
This would be more like Shrock.
Heteroatoms attached to the carbene are more...
Or like Fischer.
Fischer, okay. And then iridium, late or early metal?
Late.
Okay. So we've got a metal argument and a substituent argument, both in the same direction. So what will we call this?
See, like in my head, I'm thinking of like a Lewis structure where I would push down the electrons from oxygen and then the two from the. Is that the correct way to think about something like this?
Well, you can. I think sometimes it's helpful to maybe just draw this like. So here's your carbene, your singlet carbene. And then you have this open p orbital. And then you have this group, which can stabilize the open p orbital, the singlet carbene. But that's probably how I would kind of represent it. I guess you're wanting to see it as being very alkyl-like because of the pi donation and think of that resonance form. Is that right?
Yeah,
Carter?
but that's not correct. Okay.
Yeah.
I see. So then coordination number would be 4, and then
Okay.
iridium would be, I guess the Fischer carbines are like L, so it'd just be iridium 1.
Okay, 4 L's, Fischer, iridium 1. We have this, we see it's +1 here. I'm going to delete all this because it's just making it too busy. Iridium 1, so you said, and that's D what?
D8.
D8, okay. And then 4 L-type ligands, 8 electrons. That would yield us a what? What'd you get for this, Carter?
16.
Oops. Okay. Any questions on that? Super, Carter.
Okay, thanks for clarifying about I guess the way it's drawn makes me want to push electrons like an enolate.
Fight the urge. Fight the urge, Carter.
Yeah. Okay. Thank you.
Okay. How about the next one? Tiffany.
So 1, 2, 3.
A lot going on this one. So let's just take it one step at a time. Don't panic if you're
okay.
Let's first just inspect this carbene part of it. So what are we thinking for the carbene?
If there's, I guess, not a heteroatom.
No heteroatom, okay.
That would suggest like more of a Shrock type.
Okay. And the metal here, do you want to call this early or late?
Oh. Late.
Yeah, this one is kind of a trick. It's a little bit in the middle, but I guess in the grand scheme of carbines, we'd maybe call this early. And then I think if you dig in, then you would see that you've got multiple X-type ligands here. So it's going to be high oxidation state. So that's another signaling element. You've got high oxidation state, and it's like a middle part of the periodic table, but we'll call it early. So what are we thinking then?
This would be like a Shrock type carbine.
Okay. Okay, and now we can do some of the easy ones. We can do, maybe we'll go assign all the ligands first, and then the oxidation state of the metal is probably the best way to do it.
Sure.
So you've got this glyme. What's that?
That would be 2, or I guess 4 electrons.
Yeah, so 2 L type.
Yeah.
And then you've got 2 chlorides.
2 X type.
Okay. And then now we've got to deal with this creature. drawn as linear. So a linear amido, we saw are what, Tiffany?
LX2, is that right? So 6 electrons?
Yep. Okay, so now let's count up our X type. We got 2, 3, 4, 5.
Mm-hmm.
Which is going to be D what?
Oh.
Oh, sorry. So maybe oh, sorry. I'm confusing everybody. I just counted this 2x as 1x. Should be tungsten 6, right? That's why I'm getting puzzled looks.
Yeah.
Okay, which is D what?
0.
D0, and then let's count up all of our ligands. 2, 3, 4, 5, 6, 7, 8, 9 ligands. Should be 18 electrons. And then we add it together to get overall 18 electron. And then the coordination number, this is maybe a little bit less meaningful in this case, but as we define in the class, the number of electron pairs engaged in bonding, we would go through and say, okay, 2, 3, 4, 5, 6, 7, 8, 9. Is that right?
Yes. Yeah.
Curie, would this still be considered octahedral in shape, even if it's coordinate 9?
I think this is octahedral or distorted octahedral.
Okay.
Again, I have to say this is one where the coordination number is maybe not super meaningful. Like as we defined in class, we arrive at that solution, but in terms of the number of ligands, it's 6. So okay. That's maybe more meaningful and think about geometry.
Okay.
Is that a fair explanation, Tanner?
Yeah. Yeah, for these types of things, you don't necessarily need to worry so much about the trying to classify the geometry under canonical octahedral terms.
I lost my sharing window somehow. Okay, get it back. Okay, any questions on that? Oh, the first example, I almost missed this. The first example comes from our chemist of the day from last time, day 7, who is, I don't know if anybody recognize him. I'm not hearing anybody. This is Nathan Schley from Vanderbilt, who does a lot of interesting work with these iridium pincer complexes and reactions of that involve the intermediates of the type shown, and also other chemistry like carbon silicon and silicon hydrogen insertion reactions, and he was educated first at Davis and then PhD with one of the last PhD students actually in the lab of Bob Crabtree at Yale, postdoc with Greg Fu, where he I think made a name for himself by carrying out what is really the most comprehensive mechanistic study of the Fu type asymmetric cross-coupling reactions, and then has launched his independent career roughly the same time as me. Okay, so let's jump in now to underlying principles of catalysis. Hopefully now we have a good foundation, structure, bonding, elementary steps. And the theme that you're going to see again and again and again in this part of the class and then future lectures is that we're going to have a metal that's going to engage some organic substrate, and then some string of the same elementary steps that we saw: oxidative addition, migratory insertion, reductive elimination, spitting out now a new product, and then the catalyst, the metal complex used in catalytic quantities being free to engage a new molecule of substrate. So I do want to take just 1 or 2 minutes to define rigorously some of these concepts that you have all heard before, just so that everyone's on the same page, and so some of the subsequent points that I'll make will be crystal clear. So this, what is shown here, I'm sure everybody knows. You don't feel obliged to write this down by any means, but as we know, a catalyst is a substance that that does not affect the thermodynamics of a reaction, but lowers the kinetic barrier by which that reaction can take place, and it accelerates a reaction rate without itself being consumed, as defined by Oswald in the late 19th century. And so just to define that rigorously in terms of delta H, delta S, and delta G, here's a comparison of just a generic A plus B goes to C plus D reaction in the presence and absence of a catalyst. The absence of the catalyst shown in black. And the key point here is that delta H, delta S, and delta G do not change. And this is back to Gen Chem, but it never hurts to remind ourselves this. So the thermodynamics are determined by the molecular connectivity, as well as things like concentration, pressure, temperature. And then the reaction rate is determined by delta H, delta S. And then one of the, in terms of reaction rates, one of the themes that we saw in the migratory insertion lectures is that it's important to be rigorous. And when we're talking about rate acceleration effects, what is the origin of that? Is that a ground state destabilization effect? Or is that actually a transition state stabilization effect, which are not the same thing? And a reaction can go faster for either of those two reasons. So let's just take a look at this generic catalytic cycle. I took this from the Hartwig textbook, and I like it because it's generalized enough that we can make some broad statements, but actually has some specific details that I think sometimes get glossed over, and particularly in a graduate class, we want to make sure that we're talking about rigorously. So, most catalytic reactions that we study in this, that we use and that we'll see in this class, the chemical entity that we put in, the organometallic reagent or catalyst, is itself not the active propagating catalyst. It is a pre-catalyst more often than not. And so often when we draw a catalytic cycle, there are actually some hidden steps that aren't defined. Where a catalyst precursor needs to undergo some activation steps. I'm just drawing this in the most generic way possible. So just as an example, let's say we're doing a cross coupling and we use palladium acetate plus triphenylphosphine. Then palladium acetate is not the active catalyst. You need to get to some palladium zero phosphine complex. And so some series of events, and we'll talk about this more in the cross coupling lecture, need to happen to get it on cycle. And then in that case, where you probably have excess ligand, now immediately there's an off cycle process that is going to be reversible, where extra ligands can bind to the metal. And this is not necessarily deleterious. It can actually be helpful for stabilizing the metal and increasing the overall TON, but would come likely at the expense of the TOF, turnover number, turnover frequency, two terms we'll define rigorously in just a moment. So once the and you know, I think this step or series of steps often neglected, but we'll cover this on problem of the day #1 because I think it's important to make a point of. So then now you have your active propagating catalyst that will bind some substrate molecule. This could be via, let's say, you know, pi coordination to a filled pi bonding orbital, for instance. And then here too, a commonly encountered scenario is that you can get off-cycle species that would arise from multiple things. What Hartwig draws here is a non-productive dimerization of the substrate catalyst complex, again, reversible. Alternatively, you can have a non-productive form of the catalyst that it contains 2 molecules of substrate. So the catalyst's got to get this just right here most of the time. It needs one substrate molecule. Now some elementary step happens, not defined here, that transforms the substrate organic fragment to now a new intermediate that's still catalyst bound. Here too, there's another opportunity for things to go wrong. You can have catalyst decomposition at this state. So this is drawn as irreversible. As an example, this could be, let's say what you're trying to do is a diarylation reaction, something that we do in our lab. But once you get to your, after post-migratory insertion, after you get to an alkyl metal intermediate, undergoes beta hydride elimination, that makes a metal hydride, and that metal hydride is you know, formally reduced and then can't get back on cycle. That's a way that you would deactivate through a metal bound intermediate. But if all goes well, it will continue forward, transform to the desired product by some other step. Sorry, these are not helpful annotations, I realize. And then dissociation of the product to close the catalytic cycle.
Hey, Kiri, could you talk a little bit about the reversibility of the closing of the catalytic cycle there? Like from your catalyst and the product bound to your catalyst? Why does that go back and forth?
Yeah, I mean, you have no reason to expect one way or the other. It's drawn here, I think, probably to imply that there's another complicating factor, which is in some cases you can have product inhibition, where the product can come back on, coordinate the catalyst, and sequester it. In this case, it would be sort of on cycle, but in the wrong part of the cycle, potentially, if that makes sense. But in the absence of more information, that step is you know, not inherently reversible or inherently irreversible. Okay, let's jump over then to problem of the day #1, which applies things that we've already learned to this challenge I mentioned of getting getting on cycle. So I'll share this very briefly, but I also have these structures sketched out. Give me 1 minute here. It's never a class, never an online class goes by without some new technological mystery. Okay, there we go. There is Nathan, our day 7 chemist of the day. Okay, so this is the reaction. You have this Pallada cycle drawn bearing this biaryl dialkyl phosphine ligand, treat with base, polar solvent, or ethereal solvent, room temperature, 2 new species. So what's going on here, and then let's unpack this in the context of our discussion of catalysis. Okay, Huiqi, are you there?
Yes, I'm here.
Okay, what's going on here with this
So
reaction?
I think you will form an Engle first, and the palladium is coordinate to the phosphine ligand.
Okay, you're getting ahead of yourself. So what happens when you treat this with base? What does the base do?
Oh well, eliminate the chloride.
Okay, so one possibility is ligand exchange,
Okay.
but that's probably not going to be productive. So what else? Are there any like acidic protons on this molecule?
The proton on the nitrogen.
Okay. Normally we wouldn't say these are acidic, but they're bound to a metal, and the metal is Lewis acidic in nature. So now you have some lowering of the pKa. Okay, so we deprotonate. Now you have two X-type ligands. Palladium here, if you do your electron counting, you'll see it's +2 oxidation state. You have two X-type ligands. The third X-type ligand that is not tethered through chelation now is going to be, that coordination is going to be destabilized. So we'll draw that as leaving and having an open coordination site. Now you have a 3-coordinate species, which as we had discovered, or as we had discussed before, is primed for what Huiqi just said, which is reductive elimination to give her favorite heterocycle, the indolene, along with, I think you said, palladium bound to ligand. Now, how's that going to look, Huiqi, this palladium ligand?
I think the palladium should coordinate to the phosphine and the oxygen.
And the oxygen, okay, that is certainly a reasonable possibility. Let's draw this out. Any other possibilities you considered? Anything else could happen here, Huiqi?
I have no idea.
Anyone want to jump in for an assist?
Yeah, aryl migration.
Aryl migration. What aryl migrate?
One of the CYs.
The CYs.
On the phosphine?
I don't, well, those are alkyl, the cyclohexyl. I think that they'll undergo pretty slow migratory insertion or anything like that, or oxidative addition. Anyone else have idea?
The dimethoxybenzene itself, the benzene ring pi system.
Yeah, okay. Was that Feng? Thank you, Feng. So let me redraw this in my attempt to convey 3-dimensionality. So there's an interaction that can happen through the ipso p orbital here. It's a little bit hard to see in 2 dimensions, but I promise if you draw this, if you look at the crystal structure, you'll see that the metal is sitting right over the face of the second aryl of the biaryl. And so there's a productive stabilizing interaction that can happen there. Very good, Feng. And that's a common design feature of this ligand class. And I think as Huiqi mentioned, that these that do have flanking 2,6 heteroatoms also have this other possibility of being able to adopt, of those groups being hemilabile. Hemilabile just means, you know, being able to coordinate in a bidentate fashion and then potentially swing off. Okay, super, that's part A. And then part B asks, how would you make this thing? Any thoughts here, Stone?
Just cross couple.
Cross couple what?
Maybe the two like the Nagisa reagent on the bottom with the
okay, you're talking
bromide
about
on top.
the ligand here first. Okay, let's
Yeah.
tackle the ligand. So Stone's saying let's cross couple it, and you want to do, I'll draw this out, some metal here. You said Nagisa, so organozinc, and then some halide here. Is that right, Stone?
Yeah.
And what potential problems could you see from this, if any?
It's like just too hindered.
Yeah, these 2,6 di-substituted coupling partners are always tough. I think particularly organometallics that are 2,6 diheteroatom substituted, I think undergo pretty rapid proto-demethylation oftentimes. So you've got a hindered coupling, which could be challenging, but it's not, certainly not unreasonable a priori. Any other thoughts?
Maybe like product inhibition, or like
product inhibition could be an issue as well. You're making a ligand that itself we know is a strong metal binder. Anyone want to jump in for an alternative approach if you had a different thought than Stone? Camille, any thoughts here?
I was thinking, well, for the ligand synthesis?
Ligand synthesis first.
Yeah, I was
That's
thinking similarly to Stone.
Okay.
Could you switch the coupling partners?
You could, that might help. Most of this family of ligands, so these are, probably most people know this, these are Buchwald ligand family. A recurring problem is, the power of these ligands stems from having this crazy steric substitution, but a problem then arises in their synthesis, which is that they're challenging to make. And I think the common way to make them is sort of interesting, which is why it merits some discussion. It connects to what Stone had told us, which is you're going to use some metallated, typically Grignard or organolithium, bottom half. You add it across in situ generated benzene. Benzene can be generated from many possibilities, but I think often they generate this from the 1,2 dihalo version. Not always, but. And then upon benzene addition, you get a new organometallic that they then can couple further with this. I'm doing this shorthand here just to save time. This is not necessarily all a one pot sequence. Under the action of catalytic copper, then they can install the phosphorus there. And I think in some cases it requires an intermediate X plus quench before the copper coupling. But that's the general sequence: is generate benzene, react through the benzene, and then couple out. Okay, and then Camille, what about the synthesis of this? Now that we know how to make the ligand, what about synthesis of the complex?
You could start with the palladium 0 and the aryl chloride with the amine on it.
And what do you like for your favorite palladium 0 source?
Palladium, is palladium DBA? please?
Palladium DBA. Great. Lots of different options here. One that I think Buchwald has used a lot subsequently is this one. It's actually palladium 2, but upon reductive elimination is then becomes palladium 0. Lots of different palladium 0 sources here, so none are wrong a priori. Okay, and then let's just finish up this discussion. So this is the so-called G1 Buchwald precatalyst for cross couplings and Buchwald Hartwig aminations. What would be an advantage of this based on our previous discussion, Daniel?
Sorry, I don't think I caught the question. The D1, you said D1 precatalyst?
Oh, G1. So this is a common, this complex is a common precatalyst for Suzuki cross couplings. So upon treatment with base or Buchwald Hartwig aminations, you can get to this species, and that's the active catalyst. Remember, we talked about how to get on cycle. So why might this, just spitball in here, why might this be advantageous as opposed to, let's say, just adding palladium 2 DBA3 plus this ligand? No right or wrong answers here. Anyone want to chime in?
So,
Aaron, what do you think? Oh, sorry. Go ahead, Dane.
I'm maybe thinking about this the wrong way, but I mean, like it's already bound. Like the oxidative addition, I would assume would be rather rapid, and so that can.
Yeah, I think you're hinting at the right thing here, which is that now you have a nicely bound 1-to-1 metal ligand complex that is exactly
so
in
then
the state that you want it.
Stoichiometric, you're saying, or
yeah, well, for the what I'm saying is that this complex is often used as a precatalyst. So in that sense, it's used catalytic, and the reaction that it's used for as a precatalyst are things like cross couplings. And so, as you rightly pointed out, advantage is that it gives you nicely well-defined, reliably ligated 1-to-1 metal ligand for that application. Anyone want to add anything else? Or what about a disadvantage? Any thoughts, Aaron? Advantage or disadvantage? Any thoughts there?
I know an advantage is that it's because you have this hemi-label second phenyl ring, you disadvantage beta hydride elimination, so more likely to actually get the cross coupling you want.
Yeah, I mean, I think that you're talking there about why the ligand would be useful in cross coupling, but I'm talking more about the use of this as a precatalyst as opposed to other precatalysts that you might use.
Would you expect it to be? Would you expect it to be more air stable because this palladium is 2? And I guess a disadvantage of that is like you would have to make it. I don't know if Sigma would have it.
Sigma does have this, but you have to make it, and
yeah.
And then
I guess
An advantage if you're the Buchwald group is they have the patents for it. And if a disadvantage, if you're not the Buchwald group, is you have to pay the Buchwald group for the patents.
I guess another disadvantage is like you just want to just throw in your catalyst already without having to activate it.
Sure, sometimes the base activation might be a problem.
Yeah.
Another commonly quoted disadvantage in these is that the byproduct can actually be an inhibitor. We talked about various things that can inhibit. And indolene is not the most chemically benign entity, as you all know. So there have been subsequent generations that the Buchwald lab has built out to make things that are byproducts that are less inhibitory. And they have 4 generations now of these. I think the 4th generation one generates what is the most benign byproduct, which is this methyl carbazole. Okay, a lot to unpack there. So if some of it seemed kind of fast and furious, we'll come back when we talk about cross coupling, and so don't worry. Just want to get the key points, which is different strategies for dealing with this catalyst activation step, and then the key elementary steps involved for how you activate it and how you would eventually make it. And then the chemist of the day here is a co-author on this paper that's being referenced. I don't know if anyone recognizes him from the photo.
Is it Forrest?
This is Brett Forrest. Is that Aaron? Thank you, Aaron.
Yeah, isn't he in power science, I think? Like a cross section between the two.
He is yes. Now in his independent work has been doing a lot of interesting work in polymer chemistry, undergrad at Montana State, PhD with Buchwald, where he rose to fame as a graduate student for his discovery of a ligand that now bears his name, Brett Foss, postdoc with Craig Hawker at UCSB, where he developed photo-controllable atom transfer radical polymerizations, and then now independent career at Cornell, where, as Aaron pointed out, he works the interface of organometallic chemistry and polymer science. Here's the original reference. Another first author on it is Mark Biscoe, another prominent chemist in the area of cross-coupling, in case anyone recognizes his name. Brett is the second author on this paper from the Buchwald group. Good, any questions? Okay, let's go ahead and march forward. And here we'll just define terms that we'll see throughout class. Common metrics that are used to quantitate catalyst performance are turnover number, basically the number of times you go around the circle, and that's calculated just by the moles of product divided by the moles of catalyst. And then so that's in some sense a measure of catalyst stability or lifetime. Really stable homogeneous catalysts can sometimes give you tens of thousands of turnovers. And then turnover frequency is the kinetic measurement that is turnover number for a given unit time. So the first is lifetime and the second is kinetic reactivity. And then just to continue on what we mean by kinetic behavior and how to think about kinetics of these multi-step catalytic processes. And this may be review for some, but it might be new for others. So we'll just take a minute to define things clearly. These homogeneous catalytic reactions are often approximated using steady state approximation. And so when the system reaches steady state, even though there are many steps, obviously, each step, when it's at steady state, is progressing with identical rate, though the rate constants for each step are different. And so sometimes in the literature, and I think the Hartwig book is quite rigorous about telling you what to say and what not to say. In the literature, sometimes you'll see rate determining step of the catalytic cycle, and that's somewhat meaningless because every step has the same rate as long as it's at steady state. And so the more rigorous thing for defining what the slowest step is, or the step that's sort of the gatekeeper from the circle turning around, is the one that has the highest rate constant. Is the turnover limiting step. I have smallest here, but I guess I must mean, yeah, smallest, the slowest, right? Slowest first order rate constant. And then the catalyst resting state is another term you read commonly in literature that refers to the catalyst species that's present under operating conditions in the highest concentration, and that can be an off-cycle species. So we talked about how there are reversible processes that can partition the catalyst off-cycle, and the catalyst resting state can be any of those. So when you're lucky, you can measure that directly by taking an NMR of a reaction that's proceeding, in situ NMR, and then observe what new species that's metal containing that you see. And sort of the upper bound in terms of rate is defined by now the turnover limiting step times the concentration of total catalyst in solution times the concentration of the reagents. So yeah, again, I think at first glance, this might be a little counterintuitive to people, but just think that, like, as the cycle's turning over, every single step is happening at the same rate because it's under steady state. And so when we talk about what step is controlling the rate, you have to look at the one that is where it is the rate constant is the smallest. Okay, any questions there? So most of this class will focus on homogeneous catalysis. Obviously, there's a huge body of work in heterogeneous catalysis. Society supporting technology like Haber-Bosch reaction is a heterogeneous reaction. And sometimes actually it's not clear when you design a new reaction what's going on in the flask. Is it heterogeneous or homogeneous? And we'll talk about that in probability number 2. In terms of just some general overview level comparisons of a homogeneous process versus a heterogeneous process, both obviously have their uses. I think homogeneous processes, they benefit particularly now since Wilkinson's first discovery of triphenylphosphine as a supporting ligand for solubilizing metal and enhancing reactivity in the 60s. We benefit from this ability to actually tune catalytic processes rationally through ligand design. Ligands are our hands as organometallic chemists at the transition state to affect bond making and bond breaking. And then a con that especially anybody in process chemistry will tell you is the separation. Sometimes you're using these homogeneous metals and you can't separate them from your API if you're working in pharma, which can be a huge headache and require separate steps just to scavenge metals. And then on the other side, heterogeneous processes tend to be have really good reactivity, turnover number, low cost, be recyclable. A lot of the feedstock upgrading or feedstock interconversion, like I mentioned, the Haber-Bosch process, that require extreme operating conditions like high temperature, heterogeneous catalysts are kind of the only way to go economically for those. But they lack this ability to tune. I think this is a frontier area of research. There's people who are working on, like ligands for nanoparticulate catalysts, for example, but this still remains a challenge. And so let's take a quick peek over at problem of the day number 2, which will get at this question of how do we know what regime we're in, and if we don't know, how we can figure it out. Are you able to see the screen share? I moved from one mono to the next? No. I've got to learn my lesson not to do that. Okay. Okay, so this is a reaction published by the Hartwig group. It's a unusual type of hydrogenation where you're cleaving an aryl oxygen bond, H2, nickel. They have different versions of this, different reaction conditions, but I just want to focus on these specific conditions. And I think what would strike you if you're looking at it is high temperature. There's no real supporting ligand other than TMEDA, which is a viable supporting ligand, but might not be stabilizing enough for these extreme operating conditions. So there are some reasons to suspect that this might not be a purely homogeneous process. So if we wanted to get at this question, homogeneous versus heterogeneous, what types of experiments would we do? Van, maybe do you want to do a 2-minute breakout room here so people can compare thoughts, and then we can reconvene? Okay, looks like we're repopulated here. Is my screen share working? I just added the reference so people can read more on this interesting paper. What do you think, Kelly? What's one, or if you have more ideas of how you would probe this?
Would varying the pressure of hydrogen gas be one way to tell, like dependence of rate on the pressure?
What would you expect in one or the other?
I guess if you were in a homogeneous system, you should hit some kind of saturation point and the rate wouldn't increase any further after a certain time. But if you keep pressurizing and it keeps increasing the rate, then maybe that would suggest heterogeneous. I'm not sure.
I like where you're going. I think you have to be a little careful because you can also similarly like saturate the surface area of a heterogeneous catalyst, although I think that's perhaps harder to do. But kinetics is definitely an option. I do think you might be able to get at the question that you in the way that you suggested, Kelly. But one diagnostic feature or semi-diagnostic feature is that if you look at the kinetics and there's a sigmoidal shape. So what I mean by that is the concentration of product, starting material, the concentration of starting material over time. So how fast does starting material consume? If it looks like this, and there's a period that looks like this, a strong induction period, that could be evidence that nanoparticles need to form here. As one example. Okay, great, Kelly. Anyone have anything different here? Eleanor, what about your team?
I'm not really sure. We talked about a few things. I was kind of wondering if you could try, I don't know if this would work, but if you could try to like support your catalyst on something, like force it to be heterogeneous, if that makes sense.
Yeah, this is a really interesting idea. There are multiple ways to design this type of experiment, but it's getting at something that you could call a 3-phase test. And this was developed by our senior colleague, Julius Riebeck, as a means of probing for reactive intermediates. There are different ways you could design such an experiment in this system, but one of them, for example, is you could immobilize your substrate onto a solid support. Now the substrate's solid phase. If the catalyst is heterogeneous, the catalyst is also solid phase. So you'd expect such a reaction to proceed very, very slowly because you have two solid phases that don't have any reactive interface. If it's homogeneous, we all know that, you know, reactions can happen at a polymer surface, so you expect it to be faster. And you could also think about immobilizing the catalyst, but you have to be careful whether how labile the ligand metal bonds are in that case. That would be a limitation. Anyone get any other thoughts?
I had a question.
Someone, yeah, what's up, Tim?
Change it from a symmetrical molecule and just put different substituents on each of the rings and see if it's selective?
You could, but you might struggle to know a priori what you would expect a heterogeneous versus a homogeneous catalyst to be selective for. Okay, we're running out of time here, so maybe just ask for one more idea for the audience and I can fill out this.
We also talked about doing a mercury test.
Okay, how does that work, Nathan?
I think that in a heterogeneous system, like the mercury could poison the surface of the metal particles, and it wouldn't work at all in that case. But in case of a homogeneous system, you would still expect it to work to some extent.
Beautiful. That's a common experiment. We've done that before in our lab. It's not so trivial these days to get your hands on elemental mercury, but we have some from the chemical museum we inherited from Julius Riebeck. And then another, basically the opposite of a mercury drop test is the experiment shown here, where you add dibenzocyclotetraene, and that is a strong metal binder and inhibitor. You'd expect to see inhibition of kinetics, but only in the homogeneous case. And then the last one you could do is TEM imaging to look for nanoparticles. And then of course you could re-isolate those nanoparticles, subject them to reaction conditions and see if they're competent catalysts. And I think in the Hartwig paper, if I'm not mistaken, these are the two experiments that they actually did to support that it was indeed a heterogeneous process. Okay, we'll stop now in respect of those who need to get to heterocycles, a minute over, sorry about that. And we will reconvene next week. Thanks everybody, have a good weekend.